Performance analysis of multiple intake design methodologies for an open-wheel race car vehicle using different simulations. Abstract. This paper deals with the performance characteristic comparisons and improvements achieved in the intake manifold designs in consecutive seasons for the development of formula-style open-wheel race car, by the adaptation of new methodologies to predict and control the performance characteristics as required, keeping the requirements in reference to the track and other dependent boundary conditions as well as the driver's feedback. The goal of adapting new methods was to compare how different methodology of designing the parts of the intake system, i.e., restrictor, plenum, runner, and throttle body, influence air mass flow rate and pressure fluctuations, resulting to the obtained engine power and torque characteristics. All the previous and current designs of the parts of the intake were flow tested by simulation using ANSYS Fluent and Simscale Cfd. For performance characteristics, the entire engine setup with the intake manifold was simulated with the help of 1D virtual engine simulation program Ricardo Wave, to fully compare the two intake designs between each other with the stock engine performance characteristics to measure the amount of gain that is achieved from the previously generated design with the new design, and stock performance characteristic of each part of the intake was compared with different methodologies to find which one is the most effective one to gain maximum performance. In the end of the comparisons, all the values were compared and tallied with the virtual performance characteristics of the stock engine. Keywords: Formula Student, FSAE, Intake Design Methodology, KTMRC 390, Intake Comparison, Throttle Body, Restrictor, Plenum, Runner, Ricardo Wave, ANSYS Fluent, CFD, Simscale, David Vizard's Rule, Acoustic and Reflective Wave Theory, Volumetric Efficiency, Convergent Divergent Nozzle, Helmholtz Resonator Theory. Introduction 1.1. Intake Manifold. 1.2 Constraints. 1.3 Consideration. The intake manifold is a very essential element of an internal combustion engine. The performance of the engine depends on a huge variety of factors, one of them being the design of intake manifold. The function of this is to optimally distribute equivalent amount of air to a cylinder. One of the major factors that affect the airflow inside the air intake system is its own shape. With the use of modern-day computer-aided methods like computational fluid dynamics, it can be simulated for understanding and studying the nature of airflow inside the intake manifold. In Formula SAE, FSAE here onwards, for manufacturing an open-wheel race car, the Rules Board have adopted and mandated a rule, which is, every team has to use a type of engine restriction device with its minimum diameter of no more than 20 mm, and the placement of the same should be in between the throttle valve and the engine inlet port. Due to this restriction, considerable amount of pressure drop is observed, and to minimize this loss of airflow to the engine, plenums are used to accumulate and normalize this air so that there is least surge in the airflow to the engine. The major idea of designing the intake manifold for FSAE application is to design it in such a way that the effect of the intake restriction to the intake airflow is minimal so as to counter the pressure drop in the restrictor. To support this effect, a plenum or air reservoir is used, which basically minimizes the pulsating airflow through the restrictor. So, the volume of the plenum is most important while considering the design of the intake manifold of the engine. Also, the design of the port and runner of the intake is also important, as it plays a crucial role in determining the torque and the nature of the power curve of the engine, with respect to the engine speed in RPM. Hence, these are the most crucial aspects of an engine intake system to decide while designing the intake for maximizing the performance output of the engine. Therefore, the main motive behind this analysis is to compare the performance of the two different intake manifolds, keeping in consideration the similarity of design and method of manufacturing of both. 120 mm restrictor should be placed between the throttle body and the engine intake port. 2 should be inside the roll envelope of the car. 3 no more than 710 cubic centimeters engine can be used. 4 the engine should be a 4-stroke engine. Engine selection, internal combustion engine. Salient features. General engine details, model, KTM 390. 1 single cylinder DOHC. 2 4-stroke. 3 liquid-cooled. 4 electronic fuel injection. 5 spark ignition. Engine design specifications. 1 bore, 89 mm. 2 stroke, 60 mm. 3 compression ratio, 12.88:1. 4 effective cam duration, 4 intake, 238.0. 5 throttle body diameter, 46 mm. Restrictor type Venturi. Fig 1, KTM 390 engine. B design methodology. Fig 2, intake type 1, season 2018. Fig 3, intake type 2, season 2020. 2.1 Restrictor. It is the first and the most important restriction for manufacturing an intake of a formula-style race car, without which the same is not acceptable in the competition. Both the manifolds have a restrictor to comply with the rules, whose major motive is to cause a pressure drop so as to act as a breathing restriction to the engine. There are two approaches to the design of the restrictor, which are, either to have an orifice plate or to have a Venturi type design. The vena contracta or the throat of both the methods can be no more than 20 mm according to the rule. According to both designs, a conclusion can be made on the choice of design to be implemented to the restrictor with respect to their performance and flow characteristics as well as pressure drop characteristics. According to the design, the Venturi type has much higher coefficient of discharge than the orifice plate to a flow. Also, in Venturi design the pressure drop and design is gradual and more efficient than that of the flow of an orifice, so due to this reason the Venturi design is the most opted method for the restrictor design. Both the restrictors chosen are of Venturi type for the same reason, and multiple iterations were done for the convergent and divergent angles of the both. Finally, both had an optimized design, but differed in the mass flow rates and the pressure drop characteristics. The detailed chart for both designs has been mentioned in Table 1. 2.2 Runner. This is a very important part to the whole intake system, as this decides the nature of the performance curves which the engine will produce during running. So, there are different methodologies in determining the runner dimensions which can be applicable while designing. In the Type 1 runner, David Vizard's methodology was used, according to which the runner length can be calculated out based on the max torque RPM requirement, taking the diameter of the same to be similar to the stock diameter of the port and throttle body, which is 46 mm. From there the length of the runner was calculated, depending upon the RPM level for which the max torque peak is to be achieved. The events of open wheel racing are fully dynamics-based event, hence it is required to get a feedback from the driver about the track suitability. It was considered to be 7000 RPM for stock max torque RPM for Type 1, so the calculation according to this methodology resulted in a certain length. For Type 2 intake manifold design a different approach or methodology was considered. This time, the major topic was about the volumetric efficiency result with respect to the available air pressure wave during inlet valve open duration, so acoustic wave tuning and reflective wave theory was considered, which deals with the tuning of the runner length with respect to the reflective wave frequency and time of its presence with respect to the inlet valve opening duration. So the diameter of the runner was taken to be same from the last type, hence similar to the stock port opening diameter, i.e., 46 mm, but this time from driver's feedback the preference for max torque was required to be tuned for 5000 RPM so that it can aid to the torque output characteristic of the higher ratio final drive. Thus, the length was calculated out and quarter wave length tuning was done to finalize the length of the runner which can be accommodated to the chassis. So, these methods were followed for determination of the runner length of a stock port diameter runner. Also, a trumpet type or bell mouth type collector side design was adopted to maximize and extract out more flow by minimizing the consequent wall shape restriction losses. The trumpet was placed directly at the center of the plenum to get the full use of the velocity stack at the middle part of the flow according to boundary layer separation theory of the airflow. 2.3 Plenum. Plenum can be considered to be a big expansion volume or container which basically reduces the negative effects caused due to the restrictor to regain some of the naturally aspirated characteristic of the air to the engine. as the considered engine is a single-cylinder unit, hence its airflow characteristic is pulsating type, so while this pulsating air comes in through the restrictor and enters the plenum, it minimizes and normalizes the nature to make it near stable before entering into the runner and hence to the engine. It is hard to accurately determine the volume and shape of the plenum, but approximate volumes can be found out by both physically and through software tests, and the shapes can be optimized and perfected through iteration, simulation, and analysis done in modern computer-based fluid dynamics simulation tools, CFD, in software like ANSYS, Simscale, Ricardo Wave vectors, etc. In Type 1 intake, the stock air box volume was taken as the base volume of the plenum, and tests/simulations were done both virtually and physically to optimize the performance of the intake and also the ECU fuel lookup tables according to the performance desired by the driver. In Type 2 of the intake, the volume was considered to be roughly 3 to 10 times of the engine cylinder volume, and then to iterate all different volumes possible within this range in a controlled step. Sectional volume increase till the desired power characteristic and maximum possible volume trick efficiency was achieved using virtual engine simulation software Ricardo Wave. After this, different shape had to be considered, and each shape was iterated and simulated for both packaging and flow characteristics in SolidWorks assembly and Simscale CFD respectively, to reach a point where both parameters are considerable. Finally, this was used to optimize the ECU fuel as per the fuel characteristics of the plenum chamber to find a good balance and desired performance output. 2.4 Throttle Body. It is the most neglected part of an intake system, which turns out to be the most crucial part of it, especially in FSAE. The throttle body is the most upstream part of the intake system, and it determines the flow characteristics that the intake will have. So, the diameter of the throat near the butterfly valve of the throttle body is the most important point that determines the flow that will be achieved by that intake system. There are no well-defined methodologies to define the diameter of the intake throttle body, but by a small calculation and simple simulations we can make a close approximation of how much it should be to suffice and not choke the airflow, as well as big enough to not cause flow velocity losses in air. A CFD test can be carried out of the internal flow path of the throttle body to determine the characteristic and flow velocity that it develops, and to iterate and find out the approximate diameter outlet that should be enough to achieve it. So, in Type 1 intake, to keep things simple and to overcome cost and assembly problems, a modified version of the stock throttle body was used, where the modification was removal and sealing of the idle motor and shutting the TMAP sensor hole. So it's just a simple throttle body with only TPS output. In Type 2 of the intake manifold, the throttle body outlet diameter was calculated out by the reference RPM method, and similar dimension or close to similar throttle body was found, and its internal structure was studied in CFD tool, and also it was virtually simulated in Ricardo Wave with the already constrained manifold to find out the characteristic of the performance curve. Practically, Type 1 throttle body has enough diameter to saturate the restrictor within 50% of throttle opening. But in Type 2 throttle body, the diameter at the throat is 30 mm, which is a lower diameter, and this allows using the designed restrictor to the maximum before it reaches full saturation to get a near linear torque band. 3.1 Restrictor. Mass flow rate calculation is one of the good way to determine the efficiency and performance of a CD, convergent-divergent, type nozzle design, used here as the restrictor design. Other way is the pressure achieved at the throat of the restrictor, which plays a massive role not only for the recovery pressure that will be inside the whole intake system due to it, but also this data is also very useful for the mass flow rate determination of the restrictor. So, the general mass flow rate formula for this type of design is, equals, V, dash, dash, where Q equals mass flow rate. A1 equals area at inlet. A2 equals area at throat. P1 equals pressure at inlet. P2 equals pressure at throat. Equals density of air. So, for Type 1 intake restrictor design, the opening being of a KTM stock throttle body, its inlet diameter of 46 mm and the throat diameter of 20 mm forms up the diameter for the restrictor. Now, after simulation, at an inlet pressure of 1 bar, the throat pressure was found out to be 56,742 Pa and the density of air was 1.225 kilograms per cubic meter. So, the mass flow rate for the Type 1 restrictor came to be 0.0863 m3/s. Now, for Type 2 intake restrictor design, the opening being of a Tatton nano stock throttle body, so the inlet diameter is 34 mm and the throat diameter is 20 mm. Now, the simulated restrictor generated a throat pressure of 63,652 Pa at 1 bar inlet pressure, with the air density being 1.225 kilograms per cubic meter. So, the mass flow rate for the Type 2 restrictor comes out to be 0.0837 m3/s. Table 5, Comparison between restrictor outputs. Title. Type. Throttle pressure. 56742 Pa. 63,652 Pa. Inlet pressure. 1 bar. Mass flow rate. 0.0863 m3/s. 0.0837 m3/s. 3.2 Plenum. Engine swept volume, 373 cubic centimeters, common for both. Type 1 intake plenum volume, equivalent to stock air box value of the bike equals 3000 cubic centimeters equals 8 times the engine swept volume. Type 2 intake plenum volume, 3150 cubic centimeters equals 8.4 times engine swept volume. Reason runner selection methodology was based on quarter wave tuning and inlet valve open duration. Considering the maximum volume trick efficiency of the stock engine, which is 96%, by this volume it is later validated that this volume was ensured for 91.43% volume trick efficiency capability, ensuring a near to stock-like engine performance of the engine with restrictions. Table 6, Comparison between plenum outputs. Title. Type. Volume. 3000 cubic centimeters. 3150 cubic centimeters. Volume trick efficiency range. 85.2%. 91.43%. 3.3 Runner. Parameters common for both types of runners. Runner diameter was taken same for both, which is also equal to equals 44 mm. Stock throttle body case for better engine to runner adaptation, P1, equals 90 mm. Inlet port length, which adds to the overall calculated runner length, P2, equals 80 mm. Type 1 intake runner calculation methodology. David Vizard's rule. Tuning RPM equals 7000 RPM for max stock torque. So, by the rule equals 17.8 plus 10 to 7.0, x 4.3 equals 30.7 centimeters equals 307 millimeters. The actual runner length that is to be added to the intake during manufacturing. Calculated length equals P1 P2 equals 307-90-80 equals 137 millimeters. So, the actual manufacturing runner length is equals 137 millimeters. Type 2 intake runner calculation methodology. Acoustic wave tuning and reflective wave theory. Tuning RPM equals 5000 RPM, according to the driver requirement for endurance track. Formula, L equals, EVCD 0.25 V2, slash, RPM RV, 0.5 D. Where EVCD equals effective valve closed duration equals, ECD, equals 720-0238-0, plus 20-0 equals 5020. V equals pressure wave speed equals 1152 feet/s. D equals runner diameter equals 44 mm equals 1.73228 inch. RPM equals rotation per minute equals 5000 RPM. RV equals reflective value. L equals length of runner. So, From this the length comes out to be equals 1527 mm, which is too big a length to accommodate in the overall packaging of the car, so the fourth order reflective wave is used to get the desired length of the runner to be able to accommodate in the car, which comes to be 381.77 mm. Hence, the manufacturable length is 381.77 P1 P2. Equals 381.77-90-80 equals 211.77 mm. This way the exact runner length was found out for the max torque at that tuned RPM. Now the resonance frequency was found out by Helmholtz resonator theory. FH equals V, where FH equals resonant frequency for the max torque oscillation of air wave. C equals speed of sound equals 340 m/s. S equals area of the runner equals 1520.5308 mm2. L equals length of the runner equals 381.77 mm. V equals cubic capacity of the engine equals 373 cubic centimeters. FH equals 176.824 Hz. Table 7, Comparison between runners. Type. Runner length 307 mm. 381.77. Runner diameter 46 mm. 46 mm. Methodology. David Vizard's rule. Acoustic wave tuning and reflective wave theory. 3.4 Throttle body. So, in Type 1 intake the stock throttle body was used upstream of the restrictor for ease of adaptability and sensor retainability. In Type 2 intake the actual requirement size of the throttle body diameter was calculated to get a greater mass flow rate through the intake system, which increases the volumetric efficiency of the engine coupled to this intake. Also, restrictor saturation is at the near end of the band to use all of the restrictor potential. Formula used. D equals 154 * no of cylinders * stroke * bore 2 * max power RPM 1/267,547, where stroke equals 60 mm, bore equals 89 mm, max power RPM equals 9000 RPM. D equals throttle body diameter. So, the required diameter of throttle body outlet is equals 25 mm. According to the availability and part price in market survey, Tata Nano's throttle body was used, which had a throat diameter of 30 mm, which is the closest to the calculated value. Due to a slight increase of the diameter, the max power curve also shifts to the 10,000 to 11,000 RPM band, which was achieved by changing the RPM limiter in the standalone ECU. So, it is proven that for the flow requirement in the manifold the diameter of the stock throttle body provides to be quite big, which is good for larger volume of air causing lesser choking, but on the other hand it reduces the saturation requirement which the restrictor requires to keep it in PAR with the stock performance. Hence, the Type 2 throttle body being of the approximate correct diameter not only delivers the required flow velocity but also is large enough for air volume requirement. To not choke the flow this way, the throttle body in Type 2 is a better choice out of the two. Table 8, Comparison between throttle bodies. Title. Type. Outlet diameter 43 mm. 30 mm. Reason. For ease of design. For flatter and long-ranging torque curve. D. Simulations and results. 4.1 Restrictor. Simulation result of each restrictor. Fig. 6, Type 1 restrictor simulation. Fig. 7, Type 2 restrictor simulation. Pressure recovered at the divergent end of restrictor in intake Type 1 equals 70,740 Pa. Pressure recovered at the divergent end of restrictor in intake Type 2 equals 92,690 Pa. Hence, the mass flow rate was calculated by the use of Venturi-meter formula to actualize the maximum mass flow rate through the restrictor. Boundary common to both types of intake. Inlet pressure of both type of intakes was same equals 100 and 1325 Pa, or 1 bar, as normal atmospheric pressure. Temperature for simulation equals 35 OC, considering event atmospheric temperature. Throat pressure of type 1 restrictor equals 56742 Pa. Throat pressure of type 2 restrictor equals 63,652 Pa. Mass flow rate generated out of type 1 restrictor equals 0.0856 m3/s. Mass flow rate generated out of type 2 restrictor equals 0.0837 m3/s. Also, from the above pressure contours it is clear that the type 2 restrictor is more efficient in pressure regeneration and lesser pressure drop. Table 9, Comparison between restrictor outputs. Title. Type. Throttle pressure. 56,742 Pa. 63,652 Pa. Inlet pressure. 1 bar. 1 bar. Mass flow through it. 0.0863 m3/s. 0.0837 m3/s. Fig 8, Restrictor pressure comparison. Fig 9, Restrictor flow rate comparison. 4.2 Plenum. Simulation and result of the whole manifolds. Fig 10, Type 1 Plenum pressure simulation. Fig 11, Type 2 Plenum pressure simulation. Maximum pressure at the outlet of Type 1 Plenum equals 77,043 Pa. Maximum pressure at the outlet of Type 2 Plenum equals 93,774 Pa. This proves that the air pressure generation inside the plenum of the Type 2 intake is much better than the Type 1 plenum, which in turn proves to be better in the higher volume trick efficiency regions of the ECU lookup table to extract more performance out of the mid to high RPM range of the engine. This volume proves to be good till 91.43% volume trick efficiency of the engine, which is more than enough to extract out nearly the full potential of the engine closest to that of the stock performance out of the engine. Table 10, Comparison between restrictor simulation outputs. Title. Type. Volume. 3000 cubic centimeters. 3150 cubic centimeters. Volume trick efficiency range. 85.2%. 91.43%. Outlet pressure. 77,043 Pa. 93,774 Pa. S. Fig 12, Plenum result volume trick efficiency comparison. Fig 13, Plenum result pressure comparison. E-output comparison. 5.2 Type 1 intake performance curves. 5.3 Type 2 intake performance curves. After performing the calculations, simulations, and results that were found during comparison, the values were compared to the stock engine performance characteristics to really understand the gains that were achieved, as a result of the upgradation of design methodologies that were adopted by the team. So, a comparison has been made between the power and torque characteristics achieved in each of the three cases form the 1D virtual engine simulation software Ricardo Wave. 5.1 KTM 390 stock performance. Fig 14, Ricardo Wave stock KTM 390 engine. Fig 15, KTM 390 stock engine power curve. Fig 16, KTM 390 stock engine torque curve. Table 11, KTM 390 stock engine performance. Stock engine power output. 31.47 kilowatts at 9000 RPM. Stock engine torque output. 31.92 nanometers at 7000 RPM. Fig 17, Ricardo Wave Type 1 intake engine. Fig 18, Type 1 intake engine power curve. Fig 19, Type 1 intake engine torque curve. Table 12, Type 1 intake engine performance. Title. Performance achieved. Type 1 intake maximum power output. 26.58 kilowatts at 8000 RPM. Type 2 intake maximum torque output. 30.32 nanometers at 7000 rpm. Fig 20, Ricardo Wave Type 2 intake engine. Fig 21, Type 2 intake engine power curve. Fig 22, Type 2 intake engine torque curve. Table 13, Type 2 intake engine performance. Title: Performance achieved. Type 2 intake maximum power output. 30.20 kilowatts at 9000 rpm. Type 2 intake maximum torque output. 31.67 nanometers at 5000 rpm. Table 14, Comparison for all types. Final details. Title: Type. Throttle body. KTM 390, 43 mm throat. Tatin Nano, 30 mm throat. Restrictor. 46 mm 20 mm, 195 mm length. 34 mm 20 mm 160 mm length. Plenum. 3000 cubic centimeters volume. 3150 cubic centimeters volume. Runner length. 307 millimeters. 381.77 millimeters. Runner diameter. 46 millimeters. 46 millimeters. Methodology. David Vizard's rule. Acoustic wave tuning and reflective wave theory. Performance: 26.58 kilowatts at 8000 rpm and 30.32 nanometers at 7000 rpm. 30.20 kilowatts at 9000 rpm and 31.67 nanometers at 5000 rpm. F. Conclusion: the above-mentioned comparisons are not about the shortcomings of one type of manifold to the other but the development in the methodologies adapted to achieve better results and performance out of the same engine with lesser losses for overall betterment of the collaborated success of the team. So, these are the performance gains that were achieved by the Type 2 intake used in this year's scrutineering event, which helped towards achieving better results in the design competition of the open-wheel race car. In this way not only the desired targets were achieved but also the performance expectations were fully met. Future scope. Hope that these comparisons and methodology discussion with possible results are helpful as a one-place everything paper for gaining knowledge about FSAE type intake design for the overall betterment of the entire community interested in developing a formula-style race car vehicle.